Despite the many advantages of concrete as a modern construction material, including its high strength, low cost, and ease of manufacture, its production currently accounts for approximately 8% of global carbon dioxide emissions. Recent discoveries by a team at MIT have revealed that introducing new materials into existing concrete manufacturing processes could significantly reduce this carbon footprint without altering concrete's bulk mechanical properties. The findings are published in the journal PNAS Nexus. After water, concrete is the world's second most consumed material and represents the cornerstone of modern infrastructure. During its manufacturing, however, large quantities of carbon dioxide are released, both as a chemical byproduct of cement production and in the energy required to fuel these reactions. Approximately half of the emissions associated with concrete production come from the burning of fossil fuels such as oil and natural gas, which are used to heat up a mix of limestone and clay that ultimately becomes the familiar grey powder known as ordinary Portland cement (OPC). While the energy required for this heating process could eventually be substituted with electricity generated from renewable solar or wind sources, the other half of the emissions is inherent in the material itself. As the mineral mix is heated to temperatures above 1400 degrees Celsius, it undergoes a chemical transformation from calcium carbonate and clay to a mixture of clinker consisting primarily of calcium silicates and carbon dioxide escaping into the air. When OPC is mixed with water, sand and gravel material during the production of concrete, it becomes highly alkaline, creating a seemingly ideal environment for the sequestration and long-term storage of carbon dioxide in the form of carbonate materials, a process known as carbonation. Despite this potential of concrete to naturally absorb carbon dioxide from the atmosphere, when these reactions normally occur mainly within cured concrete, they can both weaken the material and lower the internal alkalinity, which accelerates the corrosion of the reinforcing rebar. These processes ultimately destroy the load-bearing capacity of the building and negatively impact its long-term mechanical performance. As such, these slow late-stage carbonation reactions, which can occur over timescales of decades, have long been recognized as undesirable pathways that accelerate concrete deterioration. The problem with these post-curing carbonation reactions is that it disturbs the structure and chemistry of the cementing matrix that is very effective in preventing steel corrosion, which leads to degradation. In contrast, the new carbon dioxide sequestration pathways discovered by the authors rely on the very early formation of carbonates during concrete mixing and pouring before the material sets, which might largely eliminate the detrimental effects of carbon dioxide uptake after the material cures. The key to the new process is the addition of one simple inexpensive ingredient, sodium bicarbonate, otherwise known as baking soda. In lab tests using sodium bicarbonate substitution, the team demonstrated that up to 15% of the total amount of carbon dioxide associated with cement production could be mineralized during these early stages, enough to potentially make a significant dent in the material's global carbon footprint. Furthermore, the resulting concrete sets much more quickly via the formation of a previously undescribed composite base without impacting its mechanical performance. This process thus allows the construction industry to be more productive. Formworks can be removed earlier, reducing the time required to complete a bridge or building. While the idea of early-stage concrete carbonation is not new, and there are several existing companies that are currently exploring this approach to facilitate carbon dioxide uptake after concrete is cast into its desired shape, the current discoveries by the MIT team highlight the fact that the pre-curing capacity of concrete to sequester carbon dioxide has been largely underestimated and underutilized.